Okay, hello. Think it's recording. Good morning. So continuing from last time, we discussed no, not directives, operators, right? Your
Hindi,
backtrack, etc.
gamit niya. Gamit niya Lloyd. Prototype.
Hello.
Habol.
Sorry.
Yung habol yung tax ko, yung ginaano, puta ko ba akong siguro.
Mhm. Pakimute lang if you don't. Anyway, sige. So for today, we'll be talking about control structures in assembly. So your if, like how is your if else implemented in assembly, as well as your looping, your for loop, your while loop, do while, etc. Sige. Sige, let's start with okay, high-level languages will provide you with well, high-level control structures such as your if statements, your for loops, your while statements, and in some cases may switch case pa, no? But assembly, we don't have such complex control structures, and instead we have to rely on the go-to or the jump, where when you use this in high level codes, it's not really advisable to use it, no, your go-to functions, because it messes up your code flow and usually results into what we call spaghetti code. No, it's harder to trace with the go-to functions or your jump functions. So for high-level languages, it is better to structure it logically without using your go-to functions. But in assembly, we don't have that luxury. So instead, we rely on your infamous go-to and jump functions to implement such control structures. Okay, so going with the first one, sige. Uh, it's possible to write structured assembly language, but the design and programming logic using familiar high-level languages, and then we just translate the logic into the appropriate assembly language. Okay, so it says here control structures decide what to do based on comparisons of data. So similar to high-level languages, right? We usually say, for example, if x equals 0. So we are comparing the value of x, which is a variable, if it is equal to 0. Or we say if x less than 5. We are comparing the value of x uh, to 5, if it is less than or not. So it is based on comparisons of data. In assembly, the results of these comparisons are stored in your flags register to be used later. In your 8086 architecture, which we use, we are provided with a CMP or the compare instruction. So CMP is the mnemonic for compare. And this will set some flags in your flags register. Uh, this is based on the difference between two operands. So we are actually performing subtraction, as we'll see later on. So the operands are subtracted and the flags are set based on the result. But different from subtraction or your sub command or instruction, we do not alter the data. We are just setting some flags in your flags register. If you need the result for the actual subtraction, then use your sub instruction instead of your CMP instruction. So again, sub, we alter the data sa subtraction, especially sa destination. But for compare, we do not alter the data. We are just setting some flags in your flags register. Okay. Starting with unsigned integers. So we don't usually use unsigned. So we usually use your signed integers, right? But for unsigned integers, so non-negative, 0 to whatever positive value, there are two flags that are set in your in your flags register that are important. One is your 0 flag and your carry flag. So again, remember, we are taking the difference between the two operands, right? So if the values are equal, so for example, 5 and 5, 5 minus itself, 5 minus 5 becomes 0, right? The difference is 0. So if they are equal, the difference is 0, the 0 flag is set. Okay? Uh, and another one, if there is a borrow, for example, 5 minus 8, so 5 is smaller than 8, right? So the carry flag will be set because we cannot perform subtraction normally. We have to borrow from somewhere. So your borrow flag, or in this case, in assembly, your carry flag will be set. So how does that work? Okay, so we have V left and V right, so variable left and variable right. So this could be registers. This could be immediate values as well. If the difference of compare is 0, your 0 flag is set. This means that your left value and your right value are equal. And your carry flag is set to 0. So ZF is set to 1, 0 flag is set to 1, and carry flag is unset or 0. If V left is greater than V right, meaning our ZF is unset because V left is greater than V right, right? So if you deduct the value of V right from V left, there is a non-zero result. So your 0 flag is unset, naka-zero siya. Your CF in this case is also unset because there is no need to borrow since your V left is greater than your V right. But in the event that your V left is less than V right, then your 0 flag is also unset because the values are not equal. If you do subtraction, it will not result into a 0. In fact, it will result into should be a negative number, right? But for unsigned, we don't do negative numbers. So instead, we just set the carry flag, meaning we borrowed something. So if your 0 flag is unset, meaning they are not equal, and your carry flag is unset, meaning your variable to the right is greater than your variable to the left. If they are both unset, then V left is greater than V right here. If your 0 flag is unset, if your 0 flag is set rather, set to 1, and your CF flag is unset, then that means both values are the same or equal. Okay. For signed integers, we have 3 flags to beware about. So the 0 flag behaves the same, right? If they are both the same, then it will result into a 0 result. However, sorry, we also have our 0 flags and our overflow flags, rather, your OF, and our sign flag. So your overflow flag is set if the result of an operation overflows or underflows. So what does this mean? So for example, we are doing comparison between negative 100 and 100. So we are only using 8 bits of memory. For example, AL and BL lang. I'll show an example later. So 8 bits of memory, the minimum number is negative 128, right? And then the maximum is 127, positive. So if we have negative 100 and 100, so it will be negative 100 minus 100. The result is negative 200. So negative 200 is over the bounds of our 8-bit value. So that case, your overflow flag will be set because we cannot contain the whole 200 value. Your sign flag is set if the result of an operation is negative. Okay. So what's the meaning behind these flags? So again, your ZF or your 0 flag is set if both are the same. Both values are equal. If your ZF is unset, meaning they are not equal, and your SF, your sign flag, and your overflow flag are the same, it means that V left is greater than V right. if your ZF is unset and your sign flag and uh, overflow flag are not the same, then it means that your V left is less than your V right. Do not forget that these instructions can also change the flag's register, not just your CMP. Other instructions can also change the flag's register. So if you have another, say, instruction like add or subtract, which will set your overflow flag or your sign flag, it will also change your flag's register, not just your CMP. So the good thing to do is if you have CMP, after that, you automatically, or not automatically, after that, you follow it with your jump commands, which we'll see which we'll see later on. So you get the proper values. So here's the reasoning for V left greater than V right now. So if SF is equal to OF, so either they're both ones or either they're both zeros, there is no overflow, then the difference will have the correct value and must be non-negative. Thus, SF is equal to OF equal to 0. However, if there is an overflow, the difference will not have the correct value because overflow, and in fact will be negative. So sign flag and overflow flag will be both one. Let's look at some examples sa registers. I will be using AL and BL in this case, no? Just for us to easily see if there is an overflow. I move the value 100 to AL and the value negative 100 to BL. And then I compare AL and BL. So as we're doing this, we see now that AL should be greater than BL because 100 is greater than negative 100. And then I will be doing a dump regs here just to see if the value is correct or if the flags are correct. So let's go to WSL and then let's compile this sample.asm. Okay. Sample.o assembly.io. By the way, your dump regs one here. This is also included in your assembly.io or your assembly input output, the include file that we need, no? So you kind of need it for debugging as well. Okay, compiled successfully. Let's now run this sample. Okay, so we see 100, right? We are just looking at the last two digits here. So 64, this is in hex. So if you evaluate this to uh, decimal, this is 100. EBX9C here, if you evaluate this, it will be negative 100. We'll see that our OF is set here, in this case. Our overflag is set. Our sign flag is also set, and we don't see any zero flags. So OF is set, SF is set, meaning OF and SF are both set, they are both one, they are equal, meaning, going back to the slides, V left is greater than V right. Okay? Let's do smaller numbers. So let's say 50 and 20. Oh, 20 there. So we know AL is also greater than BL in this case, but let's compile and let's see the flags. Okay, so in this case, we don't have SF, your sign flag, because the result here should be 30, no, positive. And overflow flag is also not set. So OF is equal to SF as well. And we also don't see a zero flag, meaning our V left is greater than V right. Okay, what if we switch? Let's go back to 100 and negative 100 just to see if there is an overflow. And we will now be comparing BL and AL to AL. So we are subtracting 100 from negative 100. So that would the expected result would be negative 200. right? So that will overflow sa 8 bits, and the sign flag, we are expecting it to be negative as well. Okay, so let's check. Clear. Oh, that's wrong. Okay, so in this case, we only have our overflow flag, but we do not have our sign flag. Because if we have negative 200, um, let me just check. I think I have it past that. Okay, so the result will overflow, no? Maging negative 200 siya. And there will be no sign flag because the last flag will be disregarded because it's overflow. And then, so OF is 1, SF is 0. So OF is not equal to SF. We also don't see any zero flag here, meaning, going back here, this will be V left less than V right. So if we go back sa code, V left is negative 100 and AL, V right or AL here is 100. So it is correct. Now V left is less than V right. Okay, so that's for your comparison. So how do we make use of the results? We call our jump functions. For our branching instructions. So these are just similar to your go-to, no? So in higher level languages, we don't use your go-to usually, but in assembly, we are reliant on these things. So we have our unconditional branch, just like our go-to. It always makes the branch, it always makes the jump, and our conditional jumps or conditional branches that may or may not make the branch depending on the flags register. If the conditional branch does not make the branch control pass, then the next instruction is executed. Okay, we'll see examples of that later. I hope that will be clearer. So for unconditional branching, so this will jump no regardless if our flags are set or not. This is our jump or JMP command or instruction. So this is short for jump instruction that makes an unconditional branch. It is a single argument and is usually a code label. May argument siya, which is code label. Code labels in this case, so for example, this one, this is a code label. So it's a label followed by a colon. That is a code label. It will jump to that instruction or to that label in the execution. Okay. It is important to realize that the statement immediately after the jump instruction will never be executed unless another instruction branches to it. We'll see how that goes later. Okay, but we have this. This is your short jump, which can move up or down 128 bytes in memory. Um, Bytes in memory, we can't really measure, or we don't have a distinct or definitive way to measure how many instructions is 128 bytes in memory. But if you have things like this and mag-over na siya sa short jump distance, your compiler will tell you or your assembler will tell you anyway. So for now, just know na we have a short jump and we have a long jump later on if we really need to. To specify a short jump, we use the short keyword immediately before the jump label in the jump instruction. We also have this, your near. This is a jump default type now for both unconditional and conditional branch. But in 80386, we have two types for our 2-byte jump. This allows us to move or up roughly 32,000 bytes. So more than our short jump, no? And then we also have your 4-byte type or your 4-byte jump, which allows us to move at any location in the code because the addressing is longer. This is the default for 386 protected mode. So our usual execution is using your default 4-byte type near jump. You also have your far jump. This allows jump control to another code segment. It's a very rare thing to do in 386. We usually just do our near jumps. Valid code labels follow the same rules as data labels. So something like this, no? This is the format. We can have small characters or small letters, and then we end it with a colon after that to signify that this is a label. This portion is not part of the name. So the name is only as assembly main in this case, and then we just signify a colon to make it a label. Parity flag here just indicates even or odd of the result. Well, you can use this as well, pero in our case, in branching, we don't really normally use this. Para lang hindi lang ta confused, if we see this dump regs and there's a PF, or what's PF, that's just parity flag. Okay, so these are your jumping instructions. We have your JZ, which will jump if your zero flag is set. We have your JNZ, which branches only if your ZF is unset. Your JO for the overflow flag, JNO, etc., etc. So you can just see this, no? Don't need to memorize it right now because we'll use it in the code later. But these are your simple conditional branching. Okay. So suppose we have this code. If EAX is equal to 0, then we set EBX equals to 1. And then else, if EAX is not 0, then we set EBX to 2. So in assembly, we could write this as like this. Compare EAX and 0. So we are comparing the value of EAX if it is 0 or not. And then if it is 0, meaning our 0 flag is set. So we call JZ or jump 0 flag set to our then block. It will jump to the then block if and only if EAX and 0 are the same value. So the execution will jump here, line 5. And then it will say move EBX 1. So we are assigning the value of 1 to EBX. However, this is a conditional branch, right? So if your 0 flag is not set, meaning it is not equal, then it will move the value of 2 to EBX and then jump to next. Jump is an unconditional branch, so this will execute regardless of flags, no? And then it will proceed here sa next and will skip this conditional branch. So then block this label. I think I have, okay. I have this. Okay. So simple assembly code, we are moving EAX, moving the value of 0 to EAX, and then we are comparing EAX to 0. So in this case, we know that EAX is equal to 0, right? And then we call JZ then block. We jump to then block if the 0 flag is set. So if the 0 flag is set, meaning EAX is equal to 0, we move EBX 1. So we assign the value of EBX as 1. If they are not equal, then JZ is not set. This jump will not execute. So then you will say move EBX2, right? We are assigning the value 2 to EBX, and then we call jump next. Next here will skip this then block, so we don't have to execute this anymore. And then I'll just call dump regs here to check. Okay, let's try to execute that code. Sample 2, okay, and then sample 2, yeah, / sample. Okay, so we can see EAX is indeed equal to 0 and EBX is equal to 1. So again, We move the value 0 to EAX, and then we compare. Since this will set the 0 flag, it will jump to the then block. So move EBX1 so that we see EBX's value is now 1. We also see 0 flag here is set, and we also see parity flag because the result is odd. The 0 flag is set, it moved EBX to 1. Okay. So what if our EAX is not equal to 0? So let's say move EAX5. Let's see what happens. Okay, so in this case, our EAX is equal to 5, right? And EBX, the final value for EBX is 2. Okay, so let's trace. So we move the value of 5 to EAX and then we compare. So it is not the same. So JZ or our J jump 0 will not be executed. So this code will not be executed. It will proceed to the next instruction. Move EBX2. So we see the value of EBX here is equal to 2. And then we say jump next so that we skip this execution. We don't execute this anymore. And then diretso siya sa dump regs, which we see here, it dumps the register values. We can't see RZF here since they are not equal. So that's how you have a simple if-else statement. However, you can also implement it like this, right? This is sort of negative logic compared to the first one. So you have move EX0, and then we compare EX0, so same lang ang first one. But in this case, we don't call JZ, we call JNZ. So jump non-zero flag, meaning we jump if they are not equal. So if they are not equal, we jump here. We assign EBX with a value of 2. Same siya na here. If they are not equal, we say EBX equals 2. And if they are equal, this will not execute. This will execute. So move EBX1, and then we call jump next so we don't execute this block of code. So same lang na siya ang result. It's just a different way of doing things. So if we try compile this, and wait now. So sample 3, right? And this should also be sample 3. Okay. Dot slash sample. So we see 0 flag is set here. So equal CEX and 0. And then we have EBX equals to 1. Okay. So this will not execute, right? Jump non-zero because our 0 flag is set. So then we have move EBX1. That's why we see EBX is 1. Okay. Any questions? Confusing ba siya? Okay lang? Sige. Let's proceed. Okay. So we have other things, right? Like greater than or equal. So this one is more complex because we are testing if they are equal. We are also testing if they are greater than EAX, okay, with 5, the value of 5. So we have 2 flags to check. So this is will be very complicated when transformed to code. I'll show this, but will not execute this. We'll go over it here. So first we compare if EAX is equal to 5. And then it says here JS, if our sign flag is equal to 1, then it will jump here to sign on, and then it will compare. It will jump again to your then block if our JO or our overflow flag is set. And then it will go here, move EBX1, meaning OF and SF are set to 1, both. So that is EAX greater than 5, right? So move EBX1, else it will go here. it will go here. EBX equals 2. So this is very awkward, very long. So it's not really a good way to code in assembly. But for if you're just using the basic jumps, then maybe you use this. But we are blessed with our 8086 architecture, which provides us with additional branch instructions that are much easier. We now have our JE and JNE, which is our equal and not equal branches. So JE, jump if equals, and JNE is jump if not equals. So these are just the same as saying JZ and JNZ, right? So if they are equal, your Z flag is set. So JZ, same. JNE and JNZ are also the same because jump if not equal or jump if not if the Z flag is not set. However, we also have things like JL, which is jump less than, which is the same as just your JNGE or your jump not greater or equal than. So something like this. We also have A for above and B for below. The complete list is like this, right? Okay. So JE or jump equals will be executed if your V left is equal to your V right. For unsigned, it's also the same. JNE if they are not equal. JL if V left is less than or not greater than or equal. But I think it's just better to use JL. It's much more simple. JLE if jump if less than or equal. So it's also the same as JNG or jump not greater. JG if V left is greater than V right. And JGE, we use this if V left is greater than or equal to V right. So we don't have to do this awkward, very long code anymore. We could just say, in this case, JGE, right? EAX JGE5. Yeah, compare EAX5 and then JGE to the proper code block. Okay. So instead of that, we do it like this. So we compare EAX with 5 and then we jump to your then block if JGE is set. So if EAX is greater than equal to 5, we move EBX 1. So we move 1 to EBX. Else we just move 2 to your EBX and then jump next to skip this execution. May chats. Hello. Kaya pa sir, buhay pa man. Okay. Sige. Okay. Next, we'll go with your loop instructions. So, assembly, we have built-in loop or your for loop-like structures, and different compared to our usual for loop. Diba usually sa for loop natin, we increment, no? But for assembly, the default is decrement siya. So the automatic counter for this is our ECX. We loop using our ECX. So depending on how many iterations we need, we set ECX to that. So if we need, for example, 10 iterations sa for loop, we set ECX to 10. So move ECX 10 before initiating the loop. We also have your loop E or loop Z. This will check if the Z flag is set. So this decrements ECX, however, your flags register is not modified. Your flags register will be modified if you have other comparisons. So this is very useful for search loops, right? So if you have like an array, for example, and you're looking for something, we can say loop NZ or break the loop, right? If we have found something that is not equal, for example. Okay, so let's turn this pseudocode to our assembly code. Okay, so we have sum equal to 0, and then we are looping from I equals 10. Again, assembly, ang default niya is decrement using ECX. So we have here I equals 10, I is greater than 0, I minus minus, meaning we are going to loop 10 times. So what we do is move EX0, we just initialize our sum, yes, to 0. And then we move the number of iterations to ECX, so that is 10. And then we have here our label, loop underscore start. So this is starting your for loop here. And then we say add EAX, ECX. This is this part of the code. Sum plus equals I. So we are adding the value of ECX to EAX, and then we loop back to loop start. The loop will automatically break if our ECX has reached the value of 0. So this will loop 10 times. This is just same as 1 plus 2 plus 3 or 10 plus 9 plus 8 until 1. So that is your loop statement. This is another way of implementing your if statements. I think I have shown this with your J and Z. But for example, we have if condition, then block, and then else S block. We have the following code, JXX, else block. So XX here in this case, so depende siya sa gusto nyong condition. So it could be JE, JNGE, depende siya. And then you jump to else block. So this is the negative logic, no? Same sa sample 2. Here in this case. Was it sample 2? No, sample 3. Here. No? So we check negative logic, right? We jump if non-zero. So we jump if not equal to our else block. Else, but if it is 0, we execute this then block, but it is not labeled. So similar lang siya here. You have a negative logic here. So that if the negative logic is satisfied, it will go to your else block. But if it is not satisfied, meaning we get what we want, we execute our then block here, and then we call jump and if to break the if statement. If there is no else, pwede man tanga diretso na ta mag kadto sa end if. Wala na siya sa else block. Pwede man. Again, else block is just optional anyway. So if we don't have an else block, we can just jump right to end if. Okay. You also have your while condition. So this one, we don't have a default while loop for assembly. Instead, we make use of our jump. So the format is like this. We have our while label, and then we have here JX end while. So this is our terminating condition, right? So if this is negative branching as well, or negative logic. So for example, our loop will break if EAX is equal to 0. So we say if they are equal to 0, we jump to end while. But if they are not equal to 0, it will just jump back to your while loop. We are utilizing our jump here. So it jumps back to your while loop and then execute, evaluate, and then end while. So this is similar to your break function or break statement rather. Okay. You also have your do while loop, which in this case, we do away with this jump. We just have JXX do. So this is the truth condition. No, we are guaranteed that the body of the loop in line 2 and 3, if you have something here, will be executed, and then it will jump to your do while loop, back to the start of your do while loop if this is satisfied. That's for your do while loop. Next chat. Marius, ang pag-redeclare sang while and end while, sir, if damo ka sang while conditions. Okay. So if you have a lot of while conditions, you label them accordingly. So you could have while underscore 1, while underscore 2. Because if we just recycle it with just one while, then mabalik siya sa part na code there, right? It's not, you'll have something like, for example, sige. You have a label while, right? And then you have like body of code here, body of code, and then your jump to while, jump to while. If you want another while loop, hindi siya pwedeng nasa while label ka man gyapon. Dapat you have to differentiate this label. So pwedeng a while one or whatever you have. And then you have another body of code here, body of code. And then if you wish to go back to this while loop, then you say jump while underscore one. If we just say jump while, then it will jump to this part of the loop. So kind of in ng execution, it will go back to this while loop instead of going back to this start of your while one. So dapat your labels are also well labeled accordingly, depending on where you want to come back sa code. But if you only have one while loop, then pwede man, and you just have this one. But if you have two, then you also have two labels. Pwede man siya, actually, that you nest these labels. So sa body of code mo, you can have another, I'll just indent it a bit, just so to, while in, just so to indicate na it's nested. So we can have a body of code here again, body of code. And then we can say jump to while in or your inner while loop, and then we can say jump while. So this is an example of your nested while loop. Okay. So the loops are actually just not built in, but just a hacky way of doing jumps. Or yes, exactly. Our loops are not built in, except for the for loop, no, because they have an automatic decrement sa ECX. So your for loop is sort of built in. Your while loop is just returning the control flow. So yes, you're correct. It is sort of a hacky way of doing jumps. Yes. Thank you for that. Okay, proceeding. Yeah, that's the end of the lecture. So we ended sa do while loops. Any questions pa? The time is 9:48. Sige. You have time for questions if you need. Okay, information overload. You can review this lecture naman because it's recorded. I'll upload it after this. But yeah, you can just replay. Then it's also useful to experiment with assembly itself. If you don't have assembly in your PCs, I suggest that you install WSL or Windows Subsystem for Linux, and then practice your assembly code here. So you may need to do other things like uh instead of installing Ubuntu from the store, you install it from your PowerShell. You say WSL dash dash install Ubuntu instead of purchasing it or downloading it from the store, because sometimes there is some errors with virtualization. What if nag-dual boot? Okay man siya. Yes. The only thing with dual boot, no, that I don't recommend is you need to sort of transfer the files or keep the files separate between your two OS. Sa WSL, you can share files. So I think it's more convenient. But if you already have your dual boot, then go ahead. Pwede man siya. When will I upload the video? After this, after we end the lecture. Sige, I think we can end our lecture here for today. So again, I'll upload the video. And then if you have more questions, you can just send me a message to Discord. Hindi ko magaling yun sa mga workaround community. Okay, so sa labs, depende na siya, no? With Sir Ryan, if if he's saying that you don't need ASMIO, then sure, okay lang. I guess that's still okay. Because ASMIO is just for dump regs and your print and your input. In that you can just work around with just basic assembly. However, I asked Sir Dave, ang staff sa Comsci, if they can sudo app GCC Multilive for all the PCs so we can have your 32-bit libraries sa labs, no? Para maka-GCC kita sa labs using your ASMIO. So we can check siguro next week if it is functioning already. But yeah, I will leave this to Sir Ryan if okay lang na wala ASMIO. Okay? Yes. I'll check again with Sir Dave if na-execute niya na ang command for all the PCs, no? As we don't have sudo, we don't have super user authority or authorization sa labs, even as faculty, no, it should be from sysadmin. So I asked them if they can, and I'll check on it maybe later or tomorrow. Sige. Sige, yeah. If you have other questions or further clarifications, message me on Discord. I assume everyone is in the server naman. So yeah, you can end the lecture today. Thank you for coming sa online class. Goodbye.
Thank you, sir.
Thank you,
Yes,
sir.
sir.
Thank you, sir.